We conclude this chapter by returning to earlier observations and tying them to the ideas we developed in this chapter. What is the main lesson to be taken from this chapter? Even under the SparseLand model, in which signals are created by a sparse representation, their estimation may result with a dense outcome. Indeed, this is a counterintuitive result, but it is nevertheless true. In retrospect, it helps in better understanding earlier observations we had. Recall the dense solution in the deep learning that ended up being the best, and recall a similar situation we have encountered in image denoising via the global thresholding algorithm. A word of caution is required here. The above does not imply that any dense solution is better. The MMSE is an intricate estimator and one that is hard to evaluate in general. Also notice that I am not definite in my claims, and I clearly say that this just might be the explanation to earlier results. Why? Because in recent years we have exposed other explanations for the density in the better solutions and its relation to something called the convolutional sparse coding model. In a nutshell, this is a special case of SparseLand for which a different notion of sparsity is appropriate. We will not cover this topic in this course due to lack of time, but we urge you to look it up by yourself. How could we use the MMSE to improve algorithms we have already discussed? First of all, this is doable sometimes, and in fact, it is already there in some cases. Consider the following examples for things we could do. In the deep learning algorithm we presented, we could have insisted on sparse solutions, but many of them, and then merging them together. Surprisingly, no one has done that yet. In image denoising algorithms that operate on patches, we could have replaced the OMP with a random OMP per each patch. We actually tried this, and the gain was small. Why? We suspect that the patch averaging brings in an MMSE flavor anyway, leaving small room for such improvement. Still, I do believe that MMSE injected to these algorithms could give a nice boost if done properly. We conclude with another proposal. Consider the KSVD image denoising algorithm. In our massive experiments, we noticed that if we divide the image into large portions and treat them separately by the KSVD denoising algorithm, the results improve a bit. This suggests that a locally adaptive dictionary could have done better than one fixed D all over the image. In fact, let's take this to the extreme, in which we hold a different dictionary per each pixel. How about this? Well, numerically this is going to be a nightmare. So how about forgetting about the training and using the patches themselves from the surrounding area as the dictionary? What is the meaning of a sparse representation over such a dictionary? We will find ourselves using noisy atoms. So the remedy is to apply MMSE. Compute many such sparse representations and average them. This sounds like a great algorithm, don't you think? Well, what we actually got is a very close variant of the non-local means algorithm, NLM for short. The NLM is described very differently in the paper that introduced it. Per each pixel, it computes a weighted average of the surrounding patches, where the weights are these exponentials. By the way, the original algorithm computes the center pixel and not the full patch averaging. Indeed, our interpretation is very different from this description, however, it is still relevant. In NLM, we perform averaging of patches and assign weights that are very similar to the ones we saw in the MMSE estimation. To conclude, we suggested the SparseLand model, and now statistical estimation gives us clear tools for handling tasks on such signals. We saw that the OMP can be interpreted as an approximation of the map, and we discovered the MMSE alternative that is based on massive averaging. This gave us an alibi for few strange results that we encountered earlier.